Speaker is Matthew Colbrook from Cambridge here, and he'll talk to us about the same topic, part 2.
Great, thank you. So I'm going to be looking at a very specific model, which is MRI scanning, and from a bit more of a mathematical viewpoint as to whether you can construct neural networks that give something that's good and also in a stable manner. So just to recall the setup, we're given some image in an n-dimensional vector space, and we want to reconstruct the image from some measurements given by ax plus e. So a is the modality, and I'm going to assume that I'm heavily undersampled, so m is much smaller than n. And of course, without additional assumptions on your model, such as sparsity, this is a highly ill-posed problem, and you can't hope to really get anywhere. So you might try to solve this via some form of L1 minimization with constraint, or a smoother version with lasso. So why might we consider neural networks for this problem? Well, neural networks are fantastic approximators. We know this from the universal approximation theorem. So for example, if we consider the map that just takes some sampled images and maps to the solution of this basis pursuit problem, then a theorem of Pincus says that if the nonlinear function rho in our neural network is not a polynomial, then there exists a neural network phi depending on A and our samples, which can approximate this solution map to any given precision. But of course, this existence theorem isn't enough. What we really need is a constructive way of getting hold of this phi. There's no point having just some neural network out there. We need to actually to get it. So in reality, what we're actually given are not images, but and the solutions, but the approximations of these, right? So whenever you're looking at a specific model, you always have noise. You can only ever store vectors to some given precision on your computer. So the model I'm going to look at is where, rather than having y and the solution psi an rho of y, I'm going to assume that I only know these to a given precision, and I only know the modality to a given precision. So this is what you can store on a computer in reality, right? You can't store, say, the discrete Fourier transform exactly. You need to take some rational approximation. But it also models a type of numerical stability. So if you can construct a neural network which takes this input and still gives you something sensible, then you've got some robustness. So the training set I'm going to consider is just these collections. And then the question is, can we train a neural network that approximates phi, so this approximation, or rather this solution to basis pursuit, using just this training data? And you might expect this to be very easy for just unraveling standard optimization problems like ISTA, FISTA, or NESTA, right? All of these compressed sensing type results say if you can compute this solution to this optimization problem, then it has such and such properties. But the problem is, how do you actually compute the solution to that optimization problem? It's not always clear. So there's a bit of a surprising result here, which says that it's not always possible. So imagine the scenario where you want k digits of accuracy. So k is a number greater than 2, and I'm only going to allow my training or my algorithm for construction L samples of my training data. And I'm going to consider approximations in some norm, and I'm going to assume my image has more than 6 pixels, which seems pretty reasonable. Then the theorem is the following. There exists a well-conditioned class of modalities A and samples that you see M, such that the following 3 conditions hold. So if you consider the neural network phi from theorem 1, which is this approximation of basis pursuit, then the first thing you can say is that there does not exist any algorithm which takes the training set and produces a neural network that approximates phi on your class to k correct digits. Okay, so it's impossible to get k correct digits, but you can get k minus 1 correct digits with an algorithm, but it can take arbitrary amounts of training to see this. And then the third conclusion is that you can actually get k minus 2 correct digits with using only L samples. So you get this weird result where it's impossible to get k digits. You can get k minus 1, but it's very, very expensive, and in fact can be arbitrarily expensive, but you can get k minus 2 digits very easily. And this is for a well-conditioned class, so I haven't cheated here by looking at some horrible thing that goes to infinity. Okay, so that's the first result of this talk, which tells you that you need to be very careful when you're looking at these types of constructions. So it's not just enough to unravel your favorite algorithm, your favorite optimization method. The theorem also holds for other problems such as lasso. So the question is, which functions can be approximated by a neural network that can be computed by an algorithm? But this is only half the story. Okay, because for numerical purposes and robustness, you have to have stability, right? If you're from a numerical analysis background, this is kind of built into you. You need to have some form of numerical stability, and also in certain scenarios to adversarial attacks. So this is where the results get a bit surprising. So I'm going to consider the same test we saw in the previous talk, but now applied to a compressed sensing type algorithm. So this isn't a neural network. This is solving lasso with FISTA. And at the top, it's perhaps hard to see, but I've taken the brain image. So this is 60% subsampling MRI. So you expect FISTA to work very, very well on this. And I've added small, tiny adversarial perturbations. And you can see that as I do so, the reconstruction becomes unstable. So these adversarial types of examples don't just occur in neural networks, they also occur in many of the standard algorithms. And you could do the same thing if you try and solve basis pursuit with, say, Chambol-Pock. You add these adversarial perturbations and then you get rubbish reconstruction. So the reason this happens is because you need to be careful in how you solve the optimization problem. So for the rest of the talk, I'm going to present one specific case where you can solve both of these issues and construct a neural network which is also stable. So the example I'm looking at is subsampled MRI. So I'm going to take U to be the d-dimensional discrete Fourier transform, and then I'm going to subsample rows of that. So this is kind of someone having an MRI scan. Let's hope they're not using FISTA or Chambol-Pock. And then the objective is to recover the image. But I'm going to need to assume some form of model, right? Because we saw that in general it's impossible unless you have some assumptions. So the assumption is sparsity in wavelet levels. So if you take most natural images and plot their wavelet coefficients, what you'll see is that most of the information lies at the coarser scales. Right, so this plot just shows the wavelet scales of this image of St. John's, and then the brightness corresponds to the size of the coefficients. So the idea is to consider a sparsity model within these different wavelet levels as a natural candidate for, I guess you could say, your manifold of images, or where your images lie. So to keep things simple, I'm only going to consider S-sparse vectors. So S is a vector, SK non-zero elements in each wavelet level, and I'm going to denote the set of sparse vectors according to this model by sigma S. So each element in sigma S only has SK non-zero entries in each wavelet level. And I'm going to consider this weighted L1 norm, and I'm going to measure distance to sparse vectors using this L1 norm. So this is the lowercase sigma Sx. So in practice, if I let W be the wavelet transform, I expect the sigma S of Wx to be small for images, right? So you should think of, for the rest of the talk, this thing here being very, very small. And I'm going to consider R wavelet levels in a d-dimensional image, and then subsample according to dyadic Fourier bands. And if you use this model, this is what you can prove. So you first of all select a probability epsilon p, and then you assume that you have enough Fourier samples to satisfy this inequality. I'll give some indication as to what this means in a second, but the important thing is you've got some sparsity in terms of the SKs, and then you multiply by some logarithmic factor, so it's a standard type of compressed sensing result. So if you assume that your matrix is set up like that, then you can, for each n, explicitly construct a neural network phi n with 3n layers, such that with probability at least 1 minus epsilon p, the following stable uniform recovery guarantee holds. So you take any image x, can be anything, as long as its norm is in some bounded ball, and any input y, and then you take phi n of y, so what your neural network outputs upon the input, and you look at the difference between that and x, and then you can show that the difference is of the same magnitude as this thing here. So this is a term that depends on the sparsity of your image x. So that's going to be very, very small for natural images, or you can consider different classes of images. You have some quantity here which depends on the number of layers, which decreases at a rate of 1 over n. And then you have a nice stability result here. So this is kind of, if this is small, then you take n very, very large. It's almost a Lipschitz type stability for your neural network. So if y is equal to ax plus e, where e is your noise, you just get an e term here. So the way to interpret this is that for sparse vectors in large n, this neural network is locally Lipschitz on your kind of manifold of sparse images. Okay, so it's stable. Up to log factors, you can show that the result I presented previously is equivalent to the Oracle estimator, where you know the positions of the non-zero coefficients. And then for an interpretation of this kind of messy condition here in terms of the number of samples, you can consider the number of samples required in each annular region of frequencies, and up to a logarithmic factor and some exponentially small terms, you get exactly the sparsity sk. Okay, so it's kind of what you expect from optimal compressed sensing. Okay, so we have this abstract theorem which says that you can construct a stable neural network for this problem. How does it perform with regards to the instability test? Well, it turns out that it seems to be pretty stable. So I spent a couple of weeks trying to break it, and it was quite difficult. It's perhaps hard to see, but I've added the same size perturbation to the images in the top row, and the reconstruction error is proportional to the perturbation error, which you expect from this term here. So you have a stable neural network, which is also more stable than standard compressed sensing algorithms for this type of problem. So just to conclude, the awesome performance of neural networks may come at a high price in terms of stability, and given the last 50 years of numerical analysis and inverse problems, this isn't something that we should just throw away, right? We need to look at this carefully. And there's likely a rich classification theory which kind of states limits on performance by balancing stability and performance. One such example was presented here, where you could explicitly construct neural networks that were stable. These neural networks aren't trained. You have to go away and actually explicitly do some analysis and construct them. And the current state of the art in compressed sensing only tells half the story. So even standard optimization methods are susceptible to these adversarial attacks. It's not just something that you see in deep learning. So the next steps will be to assess the performance of these new neural networks and try and apply these ideas to other problems. That's it. Thanks for listening.
Questions from Matthew?
Can you tell us how you find these neural trained, but you do some?
I can give you some hints. The paper's not out yet, so I won't give everything away. But I can tell you that the nonlinear function is square root. So it's a bit unusual for a neural network. but you look at a very specific type of optimization problem, which is different to these lasso and basis pursuit types.
It's not created with it?
No. It's explicitly constructed from this specific modality, and then you use the machinery and compress sensing like RIP and things like that to prove the convergence.
So it's really an algorithm, I would say. So it's a sequence of, I mean, when you say it's a neural network, it's really a sequence of operations that you apply and a composition of functions.
Exactly. Yeah.
Given.
Mm-hmm. But the advantage of unraveling it as a neural network is that it's quicker, and you can also run things like the instability test, where you need to be able to compute the gradient through back propagation.
Okay. Yes.
So, sorry, it's a rather obvious question, but does this help with robustness of classifiers? I mean, can you?
No. This is a completely different problem. So it's just the.
You can't. Okay, so.
I haven't thought about that problem. I don't know whether some of the same ideas could be used, but then that might be difficult because classification is kind of inherently an unstable problem, right? You're approximating a discontinuous function, so you might expect there to be a lower bound on what you can do stably.
Any other questions? No? Okay, so let's thank Matthew again.